Recording, I'm not on mute. Now I'm always so worried. I was always kind of worried, but. All right, change this. The tests are marked, your marks are on Moodle. We won't get them back until Tuesday because there's still another section. And of course we use very similar tests. So there's another section writing their test tomorrow. So it's kind of unfair to you guys if we hand them back and then someone gets a hold of it and is able to use it to study. So so that's why on Tuesday you'll get your test back. So you are getting them back, but your marks are posted on Moodle. Don't worry, it was not a very good test for anyone except two. And our average was only decimals off of the other section that wrote. So just not a good test overall. I will say this though, as long as you feel like you can do better on the final exam, right, then there's still hope, because what I'll do is I'll just shift the weight from this test or from other tests to the final, as long as the final is better, right? But I won't be able to do that until you've written the final, of course, right? And so, so don't let it bog you down. I know it can be very stressful if you had a bad test and you don't want it to weigh you down. I'll just pretend you didn't show up for it and then put it on the final, right? So there's still, we can still relax, right? If you're happy with your grade, then that's so good. But if you're not, it's still okay. All right, so we're just gonna do 2.6 today. Which is, so we've already talked about vertical asymptotes, right? Asymptotes going kind of in the y direction. So today we're going to talk about horizontal asymptotes, so as we head into the x direction. So 2.6, we're going to be talking about limits at infinity. And horizontal asymptotes. Asymptotes. So like I said, we've already seen vertical asymptotes. We have already seen vertical asymptotes. Bless you. And they look something, you know, like this, kind of to keep it on the same graph here. Whee! Right. And so to summarize it, right, as x heads towards a, right, any a, not necessarily 0, like in this case, f of x is heading to, I'll say plus minus infinity. Sure, let's draw one going to minus infinity. Whee! Doesn't matter, right? I just want to say that the f of x is heading towards infinity, not the x. So today we're going to change gears and let x head to infinity in either direction and see what happens. So in this section, we will let x go to plus minus infinity, right? Making room for either way. That just means become arbitrarily large, right? Infinity is not a number, but we're letting it just get huger and huger and huger. So, oops. Become arbitrarily large. Sorry, this desk is off. and see what happens to f of x or y. And see what happens to y, right? Or f of x. Remember, we can use those interchangeably, right? F of x and y. So if you find it easier to just look at a function f of x and just replace it with y, that's fine, right? So by definition, if we let f be a function, surprise, surprise, defined on some interval a to infinity, so we're just going to focus on the positive infinity for a second here, be a function defined on some interval from a to infinity, then we can say that the limit as x approaches infinity now of f of x equals L. So if we let x approach infinity and we're able to approach some number L, right, then that means that we have a horizontal asymptote. So it means that we have, or have a horizontal asymptote at y equals L, let's say. Put a pink box around this, because this is what it means to have a horizontal asymptote. You let x go to infinity and see if you can approach some number. If we think about something like, put it on this next page here. Consider the limit as x goes to negative infinity of sine x over x, and the limit as x goes to positive infinity of sine x over x. Sine x over x, let me see if I can draw. I need equal space on both the negative y's and positive y's-ish, there. We've got an open circle at 0, right? We can't divide by 0. And then it starts its kind of oscillations here and kind of starts going like that. Probably nicer than what I was able to draw, but the idea is the same, right? So here starts big oscillations and then so what we're saying here and what we're seeing is that, well, if the limit, so on this side, on this side, we can say the limit as x approaches negative infinity of sine x over x, it's going to start hugging that y equals 0, right? And so we have a horizontal asymptote here. And then on this side, on the positive end, we've got the limit as x approaches infinity of sine x over x, also equals 0. This is an example of a horizontal asymptote. This is an example of a horizontal asymptote. Let's just define this. So the line y equals L is called a horizontal asymptote. It's called a horizontal asymptote of the curve y equals f of x if either the limit as x approaches infinity of f of x equals L, right? That's the one that we already saw. But we could also have it in the negative direction, the limit as x approaches negative infinity of f of x equals L. We can even have different L's, right? In the negative direction, we might have one horizontal asymptote, and in the positive direction, we might have another horizontal asymptote, right? And so one example of that we've seen already is the tan inverse function, right? Or the arctan function. So an example of a curve with two horizontal asymptotes is y equals tan inverse of x. See if I can squeeze it in on the same page here. Kind of centered around y equals 0. Remember the inverse tan kind of tapped out at pi over 2 and negative pi over 2. So just to have them on the same page here. Negative pi over 2 and pi over 2. And then it looked something like that. And we said that this is one of the more interesting inverse trig functions, right? Because sine and cosine, the inverse of sine and cosine are only defined on that set interval, right? Between -1 and 1. But arctan, right, is defined over the set of real numbers, right? And so it makes it more interesting to work with because it's got this shape, right? It's also got these horizontal asymptotes already, right? And so what we're seeing here is on this side, the limit as x approaches infinity of the arctan of x, or the inverse tan of x, is going to be pi over 2. On the negative side, we see that the limit as x approaches negative infinity of tan inverse of x is equal to negative pi over 2. So this one's good to keep in our back pocket, right? Because it has these horizontal asymptotes that we already know about. There are a couple of other functions that have these built-in asymptotes that we need to be aware of. So I'm just going to list them and we'll talk about them, and then we'll look at some examples. So some common limits at infinity if we're looking at just y equals x is just that straight diagonal line, right? And so as x approaches infinity in either direction, right, we're going to get either positive or negative infinity depending on which side we're talking about. So the limit as x approaches infinity from the positive side of x is also infinity, which we know if the limit is infinite, infinity is not a number, right? And so we can say it does not exist, but usually we want to specify how it doesn't exist, right? It's either because the left-hand limit and the right-hand limits are different, right? So that's one way that it can't exist, or it's going to infinity and there's this, there is no limit. Right? Or the limit as x approaches negative infinity of x is negative infinity, because if we look at the graph of y equals x, right, it's just going to be this line here. And so as x approaches positive infinity, then we see that the line is approaching positive infinity. As x is approaching negative infinity, the line's approaching negative infinity, right? So we know the behavior of a straight line. The second one is also going to go to infinity, right? And so if we've got a parabola, for example, right, then we've got x to the power of 2. We can extend that to any even power, right? And we know that it's just going to keep going and going and going. There's no asymptotes holding it in, right? It's eventually, if we let x get large enough on either side, right, this parabola is going to reach infinity, right? And so the limit as x approaches infinity of x to the power of n is going to be infinity. Oops. Because remember what, so an even power of x, right, just has a, looks like a parabola, right? An odd power of x throws the, if you want to be the function, right, throws your left arm down. So if we have, I'll just put it on the side here. Y equals x to the power of n, when n is even, looks just in general something like this, right? Whereas if we've got y equals x to the power of n and n is odd, in general it'll look something like that. Depending on the n, it might get squished up more on the x-axis, right, and just kind of be more flat. Maybe I should show that here. I don't know. But in general, those are the shapes, right? And so what we see is that either way, as x heads to positive infinity, the limit's going to be infinity, right? Regardless of if n is even or odd, right? But the limit as x approaches negative infinity of x to the power of n is going to be positive infinity if n is even. And the limit as x approaches negative infinity of x to the n is going to be negative infinity, right, heading downwards, if n is odd. So just knowing what those graphs look like is going to really help you out. So you don't have to memorize these limits, right? Knowing what they look like, these functions look like, will help you out a fair bit. This one says, because remember a polynomial, even if you have a ton of terms, right, you just look at the degree of the polynomial, so the highest power in the polynomial, and that's the end behavior of that function, right? And so what this says polynomials have no horizontal asymptotes. So knowing how polynomials behave, now we're going to be so happy if we see a polynomial, bless you, right? Because we know there's no horizontal asymptotes. And so if we're letting x go to infinity in either direction, we just need to figure out which way that polynomial is going, right? And then we can figure it out. And let's talk about a third one. So far our limits have just been infinite, right? Straight lines, polynomials. So now if we talk about the limit as x goes to infinity of 1 over x, well, as a fact, it goes to 0. And also the limit as x approaches negative infinity of 1 over x is also going to be 0. And we'll talk about why in general here. So let's talk about 1 over x to the power of r, right? Letting r be just any power. Right? If we're letting x get huge, we've got 1 over a huge number, right? And so eventually, as x goes to infinity, right, 1 over a large number is going to become 0, right? As close to 0 as you can possibly get. And so we'll say that here, right, if r is greater than 0, right, is a rational number, then we can say that the limit as x approaches infinity, can I cheat and do plus minus infinity to capture both of them, or should I write them out separately? I'll write them out separately. 1 over x to the r is going to be 0, because we want to think 1 over a big number is going to be a really small number. So small, in fact, that it goes to 0 as the big number gets bigger. Right? And the limit as x goes to negative infinity, right, of 1 over x to the r. I mean, you could say negative 0 doesn't exist, right? 0 is just 0. And so, and it has the same idea, right? As you go 1 over a big number becomes a small number. And so we're going to use that quite a bit to simplify our limits. The last limit that we're going to have in our back pocket, just kind of always just, and it just boils down to knowing what the graph of it looks like, right, is e to the x or e to the negative x. And so our fourth one is the limit as x goes to infinity of e to the negative x. Well, e to the negative x looks something like this. Passing through 0, 1, we know that. so the limit as x approaches positive infinity of e to the negative x, well, that must be 0, right? It's going to approach 0 eventually. And then same idea here, the limit as x approaches negative infinity of e to the x is also 0, because if we have a look at the graph, it's going to look similar here. Goes through 0, 1, but then as we let x go to negative infinity, right, this curve is going to slope down and almost touch the x-axis, right? So it's going to change the color, but I couldn't figure out what color to use. So like I said, we're really going to leverage this, that 1 over x to the power of anything, right? Let's just talk about x in general, but 1 over x is going to approach 0, right, as x gets larger in either the positive or the negative direction, right? And so if, for example, we're dealing with a rational function, right, so a polynomial over a polynomial, then what we do, the trick that we use is we divide each of the terms by the highest power in the denominator. And that's just something that we have to remember, right? We can divide by the highest power of x in the denominator. And what you'll see is that a lot of things are going to flush out and go to 0, right? Because 1 over x goes to 0. And so oh, I remember what usually I call these LFFs, little fun facts. Little fun fact. If we need to find the limit at infinity, right, to leverage this 1 over x goes to 0, right, that's only going to be true for as x approaches infinity, right? And so you can only do this if you're taking the limit as x goes to infinity in either direction, right? But it will be really helpful. So if we need to find the limit at infinity of any rational function, remember, a rational function is a polynomial divided by a polynomial. We divide both the numerator and the denominator. We divide both the numerator and the denominator by the highest power of x in the denominator. By the highest power of x in the denominator. So it has to be in the denominator. Oops. So if we do an example, let's take the limit as x approaches positive infinity of 3x squared minus x minus 2 over 5x squared plus 4x minus 1 plus 1. Otherwise, it doesn't really matter. It's going to go to 0 anyways. So here, just making little notes, right? We said, okay, well, I've got a polynomial over a polynomial. Fine. I'm letting x go to infinity. So then because I've got this trick up my sleeve, right? Usually if I'm taking a limit as x goes to infinity, then I'm really hoping that I have a polynomial over a polynomial, right? Because then I can use this trick and things are going to be a lot easier. So now, okay, phew, if I can use it. So now I'm going to look, what's my highest power of x in the denominator? So here, my highest power is x to the power of 2. So now what we're going to do is we're going to divide each of the terms, both in the numerator and in the denominator, by x over 2. So now we're taking the limit as x goes to infinity. I'll put the equal sign over here. And dividing all the terms by x over 2, or x to the 2. So I've got 3x squared minus x minus 2 all over x to the 2. Divided by 5x squared plus 4x plus 1 over x to the 2. So each of the terms are being divided by x to the power of 2. And so now I can simplify this and say, well, the limit as x approaches infinity, 3x squared divided by x squared puts me just at 3, right? 3. You know what? For our first example, I'll write it all out. Minus x over x squared minus 2 over x squared. All over 5x squared over x squared plus 4x over x squared plus 1 divided by x squared. Here, uh-oh, is my pen dead? I didn't know. No bueno. My pen's dead. 3%, 4%. Come on. Can talk about it. If you cancel these, right? So now you can cancel those x squareds with the x squareds. And then the next term in the numerator, you're going to get 1 over x, right? But we know as x approaches infinity, 1 over x goes to 0, right? And so now we're leveraging that fact that 1 over x, x to any power, right, is going to go to infinity as x goes to, or sorry, is going to go to 0 as x goes to infinity. And same thing with the minus 2 over x squared, right? That's also going to go to 0. And so hopefully that's close enough. So these are going to cancel. This is going to cancel with one of those. This is going to cancel, and this is going to cancel, oops, sorry, with just the 1. So what we have, right, is we have, I'll put it on the next page, the limit as x goes to infinity of 3 minus 1 over x minus 2 over x squared over 5 plus 4 over x plus 1 over x squared. This is going to be useful, right? Because as x goes to infinity, this is going to go to 0, and this is going to go to 0. This is going to go to 0, and this is going to go to 0. So you can see how useful that is, because now I'm just left with the limit as x goes to infinity of 3 over 5. Well, the limit 3 over 5 doesn't care about where x is going. And so now our limit, the limit as x goes to infinity of 3 minus 0 over 5 plus 0 plus 0. Ha, the limit's gone. I wouldn't get 0 if I hadn't taken the limit, right? Puts me at 3 over 5. So now this says that this original function, right, 3x squared minus x minus 2 over 5x squared plus 4x plus 1 has a horizontal asymptote at y equals 3 over 5. So this means y equals 3 over 5 is a horizontal asymptote as x goes to positive infinity. Bless you. Remembering that we've only checked the positive direction, right? Something else might be going on in the negative direction. And we could check it, right? Let's use the same. So we use the same argument. Now we're just going to let x go to negative infinity instead of positive infinity. And so we can use the same argument to see if there is a horizontal asymptote in the negative direction. Is a horizontal asymptote in the negative direction. So now we're finding the limit as x goes to negative infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Same idea, right? Divide all terms by x squared. And I'm not going to show all the steps anymore because we just did it, right? The only difference is that we're letting x go to negative infinity, right? And so we get the limit as x goes to negative infinity of 3 minus 1 over x minus 2 over x squared over 5 plus 4 over x plus 1 over x squared. Right, back to that where we got to before. Again, right, these x's don't care, right? These are going to go to, so as x goes to negative infinity, right, you would change the sign, you would get 3 plus 0, but it's not going to matter, right? 1 over x to the r goes to 0, right? And so these are going to go to 0. And so now we've got the same limit oops, 3 over 5. So like I said, that's going to be a really useful trick. First thing you're going to check for is x going to positive or negative infinity, right? Because these are for infinite limits. And then do you have a polynomial over a polynomial? Or can you rearrange things so that you have a polynomial over a polynomial, right? That works too. And so we can even apply this to if we have a radical function, right? And so we can apply the same method. We can apply the same method to radicals. For example, find the horizontal asymptotes asymptotes of f of x equals the root of 2x squared plus 1 over 3x minus 5. So we can do the same thing even if we have this nasty looking radical. Right? Remembering that you're going to take the highest power of x only from the denominator, right? So the horizontal asymptotes, now we're going to remember to check in the positive infinity direction and as x goes to negative infinity. And so we'll start with as x goes to positive infinity, right? Let's have a look at the limit as x approaches infinity of the root of 2x squared plus 1 over 3x minus 5. We can still divide both the numerator and denominator by x to the power of 1. That's our highest power of x in the denominator. So we get root of 2x squared plus 1 divided by x over 3x minus 5 over x. Divide by highest power of x in the denominator. Okay. Just as a little side note here, right? We can bring the x under the square root by rewriting it as the square root of x squared, right? And so here, let's just make a little side note that 1 over x we can rewrite as the square root of 1 over x squared for x greater than 0. In our case, x is heading in the positive infinity direction, so it's definitely greater than 0. Right? One thing we have to keep in mind, though, as x is going to negative infinity later, right, is that, well, that 1 over x is actually negative now, right? And so when I do, I can still put it under the square root, but I have to make it the negative square root, right? And so that's something that I have to keep in mind. Right? And so here, it's okay because we're heading towards positive infinity, so it's just going to be the positive root. And so we can rewrite this as, what did I forget? I forgot kind of an important thing. The limit. What did I do? I got carried away. The limit as x approaches infinity. I was ramping up to write out this huge radical. scoot it over. The limit as x approaches infinity. So now I'm going to write that x under the square root. And so now I've got just this huge square root of 2x squared plus 1 over x squared. Over, and then I'll just write it as, I'm just going to cancel the x. So I've got 3 minus 5 over x, right? Simplifying the denominator a little bit already. And so I've got 3 minus 5 over x. Yeah. I know that 5 over x is already going to go to 0, right? So I can kind of, I'll keep it there until I take the limit, right? But I know it's going to dissolve, so it's not something I need to worry about that much. And so I've got the limit as x approaches infinity of the square root. Well, the 2x squared over x squared is just going to be 2 over the square root of 2 plus 1 over x squared over 3 minus 5 over x. Both of these, 1 over x squared is going to go to 0, and 5 over x is going to go to 0. Now I'm taking the limit, right? So now I'm actually letting these things go to 0. And so I get the root of 2 plus 0 divided by 3 minus 0. So my limit is root 2 over 3. So as x is heading in the positive infinity direction, right, my y is going to slowly plateau at root 2 over 3, right, having a horizontal asymptote. So therefore, y equals root 2 over 3 is a horizontal asymptote of f of x. So that's in the positive direction. Like I said, we now have to look at the negative direction. And so as x is heading towards negative infinity now, I'm just going to make a quick side note here about what we talked about. If we're bringing that x under the square root, right, we can rewrite it as the square root of x squared. Right? But now x is going to be negative, and so we have to put that on the square root. So in computing, the limit as x goes to negative infinity, we must remember that x is less than 0. Which means that if we take the square root of x squared, that's the absolute value of x, which we can rewrite as just negative x. No, my x. Right. So we have to keep that in mind, right, that we've got this negative out there. And keeping in mind that our x is going to be approaching a very negative number, very negative, very large negative number. So now if we set it up the same way, the limit as x approaches negative infinity of root 2x squared plus 1 over 3x minus 5, we can say that's the limit as x approaches negative infinity, oops, negative infinity, dividing both the numerator and denominator by x again, right? Same idea, 2x squared plus 1 over x over 3x minus 5 over x. But I will make a note here that 1 over x is going to be the negative 1 over x squared, all square rooted, for x less than 0. So now we're taking the limit as x goes to negative infinity of the root, the negative root of 2x squared plus 1 over x squared. So now, over 3 minus 5x, taking that same shortcut. I'm still going to simplify that numerator a little bit more. But the limit as x goes to negative infinity of the negative root 2 plus 1 over x squared over 3 minus 5 over x. Again, this is going to go to 0, and this is going to go to 0 once we take the limit. So now, if we actually take this limit, we get the negative root 2 over 3. So now we've got that kind of same situation as we had with the arctan, right? Or the inverse tan, is we've got a positive asymptote as we're heading in the positive x direction. And we've got a negative asymptote, kind of symmetric, right around the x-axis. But still, we've got this negative asymptote as we're heading in the negative direction. So therefore, y equals negative root 2 over 3 is a horizontal asymptote, is a horizontal asymptote as x goes to negative infinity. Okay. So one thing that's tricky about infinite limits is, well, infinite limits, they're going to be a little bit different than just our regular limits as x go to a, right? Because as x goes to a, we said that we have all these limit laws, right? And if you kind of flip back to the limit laws, you'll see that one of the conditions was that, well, x has to be going to a, right? So some point. So for infinite limits, the limit laws won't apply, right? Because infinity is not a number, so it won't be able to stabilize at some point. So I will say that the limit laws cannot be applied to infinite limits, right? As x approaches plus or minus infinity. There's going to be a lot of cases where it's going to be hard to see what our limit is going to be, right? Especially if we have something that we can't. So if we don't have a rational function, right, a polynomial over a polynomial, or even a radical function like we just saw, those we know how to deal with, right? So essentially, if we've got fractions, because we could even rationalize whatever we want, or there are things that we can do, right? And so if we've got a fraction, then usually we can just divide by the highest power of x in the denominator and then let things go to 0 and things are hunky-dory. So, but then there are other situations where it's not going to be as obvious what to do for the limits. And so it can sometimes be difficult to see how a function will behave as x approaches infinity in either direction. To see how a function will behave as x goes to plus or minus infinity. For example, if I give you something like the limit as x approaches infinity of x squared minus x, we can't just throw the limit on x squared and x. It doesn't really help us much, but also the limit laws don't apply, right? So if we've got an infinite limit, we can't just throw the limit onto each of the things, right? But if we think about this kind of, okay, well, if we have to wrap our head around it, x squared is larger than x, right? And so essentially we've got this large number minus another large number, just not as large. So that's going to be really hard / impossible to kind of wrap our head around, right? And so if you're finding yourself in that kind of a situation, right, where you're comparing infinity to another infinity, you have to rearrange your function, right, into something that you can actually see. And so in this case, or in these cases, we use algebra to rewrite the function. So if we go back to the limit as x approaches infinity of x squared minus x, I don't know what to do with that, right? Because we can't do anything there. So I'm going to rewrite it as the limit as x approaches infinity. I'm going to pull out a common x times x minus 1. Now it's going to be more obvious what's going on here, right? Because I'm letting x go to infinity, right? And so this is going to go to infinity. X minus 1 is also going to go to infinity. Infinity times infinity is just infinity, right? It's going to be even more infinity. So then I get infinity, which in other words, we can say it does not exist. But if it is infinity, right, you can tack on that it does not exist, right? That's always good to show off that you know that an infinite limit is, it doesn't exist, right? But you have to tell me how it does not exist. So here, right, instead of saying, oh, okay, while I'm talking, right, instead of saying, okay, well, I have to think of this really large infinity minus another infinity, I can't do that, right, because there's no structure to it. But I can say that in infinity times infinity, well, there's no other way for that to behave than to just go to infinity, right? And so that's what we do. Let's see another example. If we want to take the limit as x approaches infinity of root x squared plus 1 and then minus x, again, right, I've essentially got this infinity minus infinity situation, right? I can't deal with that. We can't deal with that. So one way that I'm going to deal with this is, well, I've got this root plus some value, right? And I know I can rationalize this, and I can slowly turn it into a polynomial over a polynomial, or at least a radical that we dealt with and we know how to deal with, right? And so what I'm going to do is I'm going to scoot it over here. The limit as x approaches infinity of the root x squared plus 1 minus x. And then I'm going to rationalize this by taking x squared plus 1, the root x squared plus 1 plus x, and multiply by the conjugate. And then I've got x squared plus 1 plus x, right? I have to multiply by 1. Okay. Rationalize. Is what I'm doing here. If I multiply this out, I get the limit as x approaches infinity of just x squared plus 1 minus x squared divided by root x squared plus 1 plus x. This I know how to deal with, right? Especially if I simplify, right? In the top, kind of the name of the game is to simplify the numerator as much as you can, right? Because, and that's why we rationalize in the first place, is to get rid of that square root. And then because we know how 1 over x behaves as x goes to infinity, right? If I can get something simple up top, and then I don't really care what is going on in the denominator, right? Because as long as I have an x there, then I know my whole thing is going to go to 0, right? And so what we get, right, is this x squared cancels with this x squared, right? X squared plus 1 minus x squared. So now I just have 1 up top here. So this is going to be, I'm still taking the limit because I haven't let it happen yet, of 1 over the root x squared plus 1 plus x. This is essentially 1 over x. 1 over x. I don't really care how many x's are in the bottom, right? As x is going to infinity, that whole thing is going to get huge. And so now if I take the limit, I know that the limit is just going to be 0. So whenever you can get it to 1 over x or something like 1 over x, then you know the limit is just going to be 0 as x approaches infinity. Any questions about that one? No. Sometimes we have to get creative, right? And say, well, I know how 1 over x behaves, right? And so that's what we kind of work towards here, is say, okay, well, I think I can rearrange this to look like something like 1 over x. The other functions, right? I know what a parabola looks like. I know what any polynomial looks like. So if I can get it to look like a polynomial, that's great. I know what e to the x looks like, right? And so I know these behaviors. And so sometimes we have to make some substitutions, right, to simplify something, and then we kind of grow it bigger to what we want. And so we will sometimes find temporary substitutions helpful. For example, if I want to find the limit as x approaches 0 from the left, well, that's not an infinite limit. I'm going to turn it into an infinite limit, just a sec here, of e to the 1 over x. I'm approaching 0, so that means I have e to the 1 over 0. I can't divide by 0, so already I know I have to do something here. Right? I know how e behaves, right? I know how e to the x behaves, but I also know how 1 over x behaves, right? And so what if I pull out the 1 over x and substitute it with just a value for now? And so if we let, something like t, x and t are our go-to variables usually. Right? If t is going to be 1 over x, right, I'm going to let t be 1 over x, because then I can look at the limit as, well, we'll have to deal with the x because I don't have an x anymore, right? But I want to look at the overall limit of e to the power of t, right? But now I want to know, how does t behave as x goes to 0 from the left? And so I'm pulling out the 1 over x, since I know the limits of e to the power of t, right? But not necessarily e to the 1 over x. So then we know that t equals 1 over x It's another one of those situations where it's helpful to know the graph, right? What does 1 over x look like? 1 over x looks like this, right? But without that curve there. This is 1 over x. Right? So knowing what 1 over x looks like, as x is approaching 0 from the left, approaches negative infinity as x approaches 0 from the left. Right? So if I'm making that substitution of t equals 1 over x, then I have to replace the limit as x approaches 0 from the left with however x is 1 over x is behaving as x approaches or approaches 0 from the left. Right? That's the tricky part. Right? So we can say that the limit as x approaches 0 from the left of e to the 1 over x is equal to the limit as t approaches negative infinity of e to the t. E to the t, remember, looks like this. Y equals e to the t. This is now our t-axis. we said that as t approaches negative infinity of e to the t, right? So if we're heading into the negative direction, then the limit is going to be 0. So we have to know how both of these functions behave, right? But that's often going to be the case, right? We know how 1 over x behaves, and we know how e to the t behaves, or e to the x behaves. And so we want to separate them and kind of work on them individually, and then we can plug them together to figure out what the limit is. Oh. How about another example? What if we have to find the limit as x approaches infinity of x squared plus x over 3 minus x? Cha-ching, right? We've got an infinite limit, so the limit as x approaches infinity. I've got a polynomial over a polynomial. I know what to do with those, right? I look at the lowest power of x in the denominator, which is just x, and then I can divide both the numerator and the denominator by both of those, by x, sorry. So this is going to be the limit as x approaches infinity of x squared plus x over x over 3 minus x over x. Okay, so this becomes the limit as x approaches infinity of x squared over x puts me at x plus x over x is 1 over 3 over x is just 3 over x minus x over x minus 1. Only one of these things is going to go to 0 now. That's going to go to 0. But this little guy, this x, is going to go to positive infinity. And that's okay. All right. So overall, right, I've got infinity divided by -1. But that -1 is going to put me at negative infinity, right? And so that's why it's important to keep that -1 on there, right? Because this is going to be essentially infinity plus 1 over -1, but infinity plus 1 is just infinity, right? But now we get negative infinity because we're dividing by that -1. Oops. So we can have, and we can show infinite limits as x go to plus or minus infinity, just like we did here. But you use the same trick, right? You find the lowest power of x in the denominator, divide all the terms by that, and then essentially, if you have a higher power in the numerator, you're going to be going to infinity, right? It's just a matter of if it's positive or negative, right? And so you can kind of tell by what your rational function looks like. Do you guys remember Newton's law of cooling? We'll do an example, talk about it. I think it's a pretty fun law. It uses the exponential function, and so it's just kind of fun to look at. And I'll start it fresh on this new page here. Just an application of these limits, because I know they kind of get lost. Newton's law of cooling. But what we'll see next day is the whole point of doing these limits and working on these limits is because the whole goal at the end of the day is to figure out what the slope of the tangent line is, right? And so we're working into derivatives, which is just the slope of the tangent line. We already looked at that, right, where we took 2 points and we moved them closer and closer together. Hey, it sounds like a limit as x approaches a, right? And so that's where we're headed. But we'll start that next day. So Newton's law of cooling or heating, it works either way, is pretty obvious, right? If you have, usually we talk about, you know, a cup of coffee or a cup of tea or something, right? And we put it in a room that's at some temperature. We all know that at some rate, right, the temperature of the coffee is going to approach the temperature of the room, right? So the limit as t goes to infinity is that the temperature is going to approach the temperature of the room, right? And so, but we've got a mathematical formula that we can use. So we say that the rate of change in the temperature of an object, so any object really, is directly proportional to the temperature difference, between the object and its surroundings. Between the object and its surroundings. So if we have a temperature denoted by capital T at time lowercase t, and that's kind of convention, right? As we use lowercase t for time, and then capital T is usually for temperature, right? Or whatever other t thing you want to talk about. So then what Newton figured out is that we can model this as T of t, right? So the temperature is a function of the time, that makes sense, is T sub s, so the temperature of the surroundings, and I'll do the definitions below later, plus, and then in brackets, T naught, so the initial temperature of the object, minus the temperature of the surroundings, right? How far away is the object temperature from the surrounding temperature, times e to the negative k times t. And so k is just the relative rate of cooling, right? And so we're going to have to find that constant k, but it is going to be constant for each object. And then times time. Here, it's helpful to remember, because we've got that e to the negative x essentially, and so we know that e to the negative x, well, e to the negative x looks like what? Like this, right? Y equals e to the negative x. And I'll say where T sub s is the temperature of the surroundings, T naught is the temperature of the object at T equals 0. Have you guys used the T naught? So if you've got a subscript 0, you can just say naught or null or whatever. 0 is fine too, T0. And K is the cooling constant, or if things are heating up, then of course the heating constant, but in either case, it's the relative cooling or heating rate. So as an example, so to figure this out, right, I need to know the temperature of the surroundings. I need to know the initial temperature. And in order to solve for K, which is what I need later on to use this equation, right, I need to know the temperature at some other point than time equals 0, right? So I need to be given, okay, after 10 minutes, for example, the temperature was this, right? So I need 2 time points, the temperature at 2 time points. So let's see here, as an example, hot tea starts at 90 degrees Celsius. And we're in the classroom, and the classroom is 21 degrees Celsius. Right? So fair enough, now I know the initial temperature of the object, T naught, is 90. I know the temperature of the surroundings is 21. And we're also told that after 20 minutes, the T is now 65 degrees Celsius. The T is 65 degrees Celsius. We're going to break this into a couple of parts, right? But even if it just asked, you know, what's the temperature after 100 minutes or something like that, you would still have to find the relative cooling rate K. So here I'm just going to break it up into parts. But part A, what is the relative cooling rate of the T? I'll summarize it as find K. And I'll add on and round to 4 decimal places. Right. If I tell you to round the answer, then you use the rounded answer for the next parts. Right. And so, okay, so we're given, like we said, we're given that T naught is 90, TS is 21. Uh-oh, I've got 22 in here, but my example clearly says 21, I don't know. Just so we can speed through the numbers, how about we change this 21 degrees to 22 degrees? Make it a little bit warmer in here. There. I'll have to remember to change that. And we're told that T after 20 minutes is 65, right? Letting T be in minutes, but that's all right. Letting T be in minutes. So now, if we take our original formula, T of T is T sub S plus T naught minus TS e to the negative KT. Plugging in our values, right, T of 20 is 65. which is going to be 22 plus T naught, which is 90 minus 22, times e to the negative k times 20. The only unknown here is the k, right? And I can solve for k. And so I have to subtract 22 from both sides. So 65 minus 22 puts me at 43 is 90 minus 22, 68 e to the negative 20k. Just rearranging. To bring that k down, I have to use logs, right? And so, but I need to get e on its own, so I have to divide both sides by 68. So 43 divided by 68. I'm just going to keep it as fraction, is e to the negative 20k. Now I can take the log of both sides, and when I say log, I usually mean natural log. I'll specify if I don't mean the natural log. That's how often it's the natural log. So the log of 43 over 68 is, and the reason we take the log is because of the log property that says, well, now I can bring that negative 20k down in front and take the log of e. Well, the log of e is just 1. And so now I have the log of that guy. And so k is going to be the log of 43 over 68 divided by negative 20. K is approximately 0.02291537947. We said we were going to use the 4 decimal places. 0.0229. So now I've got my k in my equation here, and so what I've got is T of t is, what did we say, 22, because the temperature of those surroundings is going to stay the same. Plus, and then 90 minus 22, 90 minus 22 we said was 68, plus 68 e to the negative 0.0229 t, right? Allowing for any value of t now. Part B. Any questions about that one though? Part B, now we can use this equation and say, well, what is the temperature after 30 minutes? What's the temperature after 30 minutes? Now I'm just using the formula. T of 30 is 22 plus 68 e to the negative 0.0229 times 30. Plugging things in, I get negative 0.0229 times 30 e to the power of that guy times 68. It's easier to just do it, plus 22. Puts me at roughly, because I get a decimal approximation, 56.2096478.5 degrees Celsius. Usually I'm not shy about keeping all my decimal places, the more the merrier. But if you wanted to round, that's fine. But because I asked for 4 decimal places earlier, I'd probably cap it at 4 decimal places if you're kind of doing your own thing, but yeah, it's okay. Part C, what is the limit as t approaches infinity of t of t, of the t? Put this on its new, on a new page here. Yeah. Well, if we want to take the limit as of t approaches infinity of t, that's the limit as t approaches infinity of 22 plus 68 e to the negative 0.0299t. And again, just remembering what e to the negative x looks like. Right, something like this. Now it's going to jump up to 22 plus that, right? And so now we're at 22, but the idea stays the same. And so this is going to be the limit. Well, 22 is just going to be itself, right? And so 22 just holds steady plus 68 times, and then e to the negative whatever we know is going to go to 0. As t goes to infinity, positive infinity. And so we get 22 degrees Celsius, which is what we would expect it to, right? We would expect the t, well, the t is just heading towards the room temperature. There's nowhere else for it to go, right? As we let t go to infinity. And so we can say that the temperature of the t approaches room temperature, which is pretty obvious, but maybe not obvious with the math, right? Because we are talking about limits, and we understand limits in this sense. We just haven't seen them like this before. Any questions? No questions? That's all we're meant to cover this week. So, no questions? Like I said, you'll get your test back on Tuesday after this other class has written theirs. But the marks are on Moodle. So, no questions?
That number is 0.0229.
Yeah.
But it doesn't matter.
No, because t is going to infinity. And so then it's going to,
No, I mean, that number should be 0.0229.
oh, is it? I think I've been using the wrong one. Oh, it is too. Oh, 229, 229. Oh, phew. Oh, thank you. Nice save. All right. No more corrections? No more questions? Let's get out of here. See you guys on Tuesday. Bye, guys. I know you're here and there.